Good evening.
Yeah, good evening, sir.
Sir, Arun sir shared some of your images in from Mahindra.
I'm
For the
sorry.
function that you have attended recently in the Mahindra. So Arun sir
Yeah, yeah.
has shared some images of yours.
Yeah. Saturday I was there. I think I could meet our leader Arunachalam. So I think that was nice. It was nice meeting him. But I think we'll meet in person during the midterm or the final viva, right? So on the final exam. Sorry. Yeah.
Sure, sir.
So I think most people are here, right? So shall we get started? No, sir, yeah.
Yeah, we can start, sir.
Mhm. All right. Okay. So we will continue from where we left off. So if
Seventh
we,
class.
yeah,
Today is seventh.
yes, please, yeah. So this is where we are, right? So I just locate that screen. So we were looking at the notion of stability, right? So as we discussed, the anytime when we deal with dynamic systems, there are two things that are important: stability and performance. That's true even for vehicle dynamics, right? So you and I can only talk about performance of stable systems. Okay, so that's why we learn stability first, and then we go to performance. And then the question then arises as to how do you and I quantify performance. So what do I mean by that? Let us say, we want to, look at the poles and the location of poles in the S-plane, right? So if, we consider the location of poles in the S-plane of any system, let us say, without loss of generality, we consider two poles, right? One at -1 and one -10, right? So typically, what happens is that, like as we have realized, the poles appear as exponents in the exponential term, right? This is something which you and I have already learned, right? When we study the system response. Let's say there are two poles, one at -1 and one -10. So what we are going to have e power minus t and e power minus 10t in the system response. Okay. So if we consider e power minus t and e power minus 10t, which function do you think will impact for a longer time on the system output? As we know, any exponential with a negative exponent will go to 0 as t tends to infinity, right? That is known. Okay. But if you look at e power minus t and e power minus 10t, which will go to 0 faster?
That which has a lower time constant.
Minus 10G, sir. Minus
So,
10G.
minus 10.
yeah. So among these two things, e power minus 10t will basically go to what to say 0 faster than e power minus t, right? Is it not? So what will happen is the following. So we are going to have e power minus t influencing the response for a longer time than e power minus 10t. So for this reason, the pole which is closer to the imaginary axis is what is called as the dominant pole. Okay, so these are all terms that you and I need to be aware of. Okay, so what is dominant pole? Dominant pole is that pole which is closer to the imaginary axis, and consequently which will influence the what to say the system response for a longer period of time, right? A longer interval of time. That is what is called as the dominant pole. So typically we can have a real dominant pole like this, or we can have a pair of complex conjugate dominant poles. So that is why when we look at the performance quantification, we by and large go and study the standard first order system and second order system. Okay, that's what we are going to do in the next few classes, where you and I are going to characterize performance metrics by looking at um, the response of first order systems and second order systems, right? So one may naturally get a question, hey, why first order and second order systems? Because we know that in real life, we can have a higher order system, right? Is it not, right? So what gives us the guarantee of steadying performance of a simplified first order and second order system, while that ensures that you and I are able to extrapolate it for any higher order system. The argument is this, right? So by and large, even when we take any order system, the dominant system or the dominant dynamics, what do I mean by dominant dynamics? That is those corresponding to the poles which are closer to the imaginary axis and consequently will influence the system response for a longer time are going to be either one pole or a pair of complex conjugate poles. Okay, that's why we are going to specify performance by considering their response. Okay, point number one. And the second point is, if you look at the standard inputs, right? So what are the 4 standard inputs that we studied?
Unit response, step response,
We
sinusoidal.
Correct, very good. So we looked at unit impulse, unit step, unit ramp, and sinusoid, right? So out of these 4 standard inputs, which are bounded inputs, because please note, we are looking at bounded input, bounded output stability.
My step response and sinusoidal are bounded.
So step and sinusoid are bounded. Impulse and ramp are not bounded. Okay, unbounded. So that is why, as we discussed, for the sake of stability, right, when you and I are looking at Bevo stability, we have to look at what is the class of bounded inputs you and I are considering, and what are the corresponding outputs that come from them, right? That is what we want to look at. So consequently, the performance specifications, right, are typically quantified by using the step response and what did we call the response for sinusoidal signals? We call it as frequency response, right? So now we are first discussing a big picture perspective. Why even in vehicle dynamics, people will typically look at by and large at step response and frequency response to quantify system characteristics, right? I hope the connection is clear. Okay, so this is the general theory. Okay, it is true for all domains including vehicle dynamics. So point number one, before we go into the details of today's class, point number one, any dynamic system, we look at stability and performance. Okay, that is the key thing. So stability for you and me right now is bounded input, bounded output stability. We need all poles in the left half complex. But then if you look at performance of stable systems, when you and I are looking at performance of stable systems, and we look at poles in the left half complex plane, the first thing to note is that the poles which are closer to the imaginary axis, right, are those which are going to have a longer impact on the response, right? That's something which we have seen. So those are what are called dominant poles. So typically we are going to have one dominant pole on the real axis or a pair of complex conjugate dominant poles. That is the reason why we look at the response of first order systems and second order systems to quantify performance. Now, going on further, if you look at the standard inputs that we provide, step and sinusoid are 2 bounded inputs. So consequently, when we specify performance, we look at the step response and frequency response. Okay, so first we will look at step response, then we will look at frequency response, right? So now I hope the big picture view of the what to say, the concepts that we would have studied in these lectures would be obvious to us, right? Because we essentially are going to look at the step response of first order systems to begin with. All right. Okay. So now, having set the context, like having figured out what you and I are going to learn, right, through this particular what to say module on performance specification, let's look at a stable first order system. So first order system, as we know, means the value of n is equal to 1, and the typical governing equation of a first order system is written like this: capital T times y dot t plus y of t equals u of t. Okay, this is a standard model which is used. Okay, so we can yes, any question?
Sir, I'm sorry to interrupt. One question from my side, sir. So basically, you have related the first order system of response to the system with the positioning of pole, dominant pole.
Oh,
So can you just, sir, can you just clarify more on that? I could not perceive it.
yeah. So let us say, like we have a 10th order system. Let's say we have a ride model for our car. Okay. So I derive a set of equations of motion that results in a 10th order system. Okay. So how many poles will be there? I'll have 10 poles. Now the point is, not all 10 poles will be closest to the imaginary axis, right? Very likely. So the pole which is closest to the imaginary axis, or the pair of poles which are closest to the imaginary axis, will influence the system response for a longer time. Why? The logic is this, right? Because the exponent will be smaller in magnitude, and that's why they are going to influence the response for a longer time. That is the reason we look at quantifying performance using some parameters by looking at equivalent lower order systems. See, in real life, we are never going to get only first order and second order systems, right? So we are going to get higher order systems, but you and I need to agree on some definitions, correct? So see, for example, we are going to encounter parameters like time constant. Time constants are reasonable only for first order systems, but we use it even for 10th order or 20th order system. How can we use it? The reason why we use it is because of this logic. Okay, so this is an engineering approximation. See, all of us are looking at this applications from an engineering perspective, right? So what we are saying is that, hey, we are aware that the actual system is going to be of higher order. However, we also know that we are going to approximate the response using a lower order model, which essentially corresponds to either first order or second order. Okay, so that's the logic. Okay, so I hope it's clear.
Thank you, sir.
So the typical governing equation of a first order system is given by this. The governing equation is written as t y dot plus y of t equals u of t, where t is a real number. So here, this is a one parameter model. Why am I calling it as a one parameter model? Right now, there is only single parameter, right, which is capital T. Okay, so that's why it's called as a one parameter model. So if you and I apply the Laplace transform on both sides, what happens? So we get t times s times y of s minus y0. By now, all of us should be familiar with this. And then plus y of s equals u of s, right? These are standard terms. So we apply 0 initial conditions. We get ts plus 1 times y of s equals u of s. So consequently, the Planck transfer function, which is y of s by u of s, becomes 1 by ts plus 1. So consequently, the value of n becomes 1, the value of m becomes 0, and the numerator polynomial is 1, the denominator polynomial is ts plus 1. Okay, so these are very clear. Now the poles of the system transfer function become minus 1 by t. There is only one pole. How did I get pole to be minus 1 by t? If we solve ts plus 1 equals 0, we rearrange, it becomes s equals minus 1 by t. Okay, so that's what we have. So now, for bounded input, bounded output stability, we want pole to be in the left of complex plane. So since you and I have only one pole, this pole must be a negative real number, right? That's very clear. So when will minus 1 by capital T be a negative real number? When capital T is greater than 0. So when capital T is greater than 0, we'll have the pole in the left of complex plane, and consequently, you and I will have bounded output stability. Bounded input, bounded output stability. So as we discussed, we will talk about the system performance only for stable systems. So that is why we will look at unit step response considering t greater than 0. So now, if we consider that case and we look at the unit step response means u of t is 1, u of s is 1 by s, right? By now all of us know that. And y of s becomes p of s times u of s, which becomes 1 by s times ts plus 1. Then if we do partial fraction expansion, we have two terms, right? A by s and b by ts plus 1. So if you and I follow the usual process, we get a to be 1 and b to be minus capital T. Okay, so we essentially do the partial fraction expansion in this way, right? And consequently, we get the output if we take the inverse Laplace transform as 1 minus e power minus t by capital T. Okay, so this is what we get as. Now, this is a very simple expression, right, for the unit step response of a stable first order system. So if you and I plot this on an xy plot, okay, so on the x-axis we plot time, y-axis we plot y of t. So the first observation is that at t equals 0, we start from y equals 0, and as t tends to infinity, y of t goes to 1. So this is the asymptotic value. So 1 becomes what is called as the asymptotic output as of the stable first order system, right, which we have considered. Okay, so as t tends to infinity, okay, so we wait long enough, the output will go to 1. Now, how will this output go to 1? It is given by this curve. Okay, this is my y of t curve. So it slowly increases and then settles down to 1. So there are important, terms, definitions that come out of it. If the value of small t is equal to capital T, at that point, the value of y can be found out by substituting small t equals capital T. So what will I get? I'll get y of t to be 1 minus e power minus 1, which will be 0.632. So at t equals capital T, the value of the output becomes 0.632, and this is what is called as a time constant of the system. So the parameter time constant of the system is a definition, okay, for a stable first order system. And it is defined as the time at which the unit step response becomes 63.2% of the final steady state value. Okay, so that is what is defined as a time constant. So I hope the definition of the parameter time constant is clear. Once again, this is a definition, right? So now, why is this important? We will see that the parameter time constant keeps coming back to us as we keep going throughout this course, and even in other courses, any course associated with dynamic systems. Even if you use sensors, actuators in your application, in the product sheet, typically you will see the parameter called time constant, right? That's what this is. Okay, so this characterizes the dynamic response of a stable first order system. Now, what is one related parameter which is associated with the time constant? Let us say we want to find out, let's say there are 20 of us in this class, right? So all of us are asked to design a, let's say, a brake system, okay, which we model as a first order system. So all of us have developed a brake system, right? It's going to behave like a first order system, which is stable. But now, how do I make a choice? If I have to choose one of the designs, right, I have to make up my mind on which system, which design is good, right? So to help me do that, I would also want to ask myself, hey, which of the designs will settle down to the final value in the fastest possible time? Okay, so if I were to do that, I have to essentially wait for infinite time, right? Because y of t tends to one steady state value as t tends to infinity. But we are all engineers, right? Practically, you and I can't stay till infinity, right, to see which design settles down the fastest. So what we do is that, like, as an engineering approximation, we ask ourselves, hey, how soon will the output settle down within 2% of the final output? Okay, so that's a 2% band which you and I consider. And then we ask ourselves the question, what will be the time that elapses before the output trickles down to 2% of the final steady state value, or in other words, 98% of the final steady state value. And the answer to that is 4 times the time constant. So when the time 4 times the time constant is reached, you and I can see that from the expression, the output becomes 1 minus e power minus 4, which is 0.982. So 0.982 is 98% of 1, right, which is a steady state value. And that is why generically it becomes 2% of the final value. And this is what is called as a settling time. So the settling time, Ts, is taken to be 4 times the time constant. So we can observe that the time constant of a stable first order system is the single most important parameter or metric that is used to quantify its performance, right? I hope it's clear why the time constant becomes a very critical parameter, right, for a stable first order system. Okay, and the definition of the time constant is this. Okay, so this is a stable first order system. The dynamic response is completely characterized by the time constant, but there are some variants of this model, okay, which you and I will encounter as we go to practice. So one variant is t times y dot t plus y of t equals b times u of t. Now what is the change that you and I have introduced here? We have introduced this parameter b, which is a real number, right, on the right hand side. So what change does this bring? This essentially scales the output by b. Okay, b is some real number. Okay, so the transfer function becomes b by ts plus 1. So consequently, this model becomes a 2-parameter model. Okay, so this is a 2-parameter model. What are the 2 parameters? Small b and capital D. Okay, so those are the 2 parameters as far as the system is concerned. And if you look at the unit step response, right, the output becomes b times 1 minus e power minus small t by capital T. Okay, this part remains the same. So what has happened is that the output has got multiplied by t. Okay, so I hope it's clear. Now, as t tends to infinity, the output doesn't go to 1, but it goes to b. For this reason, b is what is called as a steady state gain. So why is it called steady state gain? We essentially give a signal, a signal which is a unit step, right? So we have a signal which is of unit magnitude. You and I are going to get an output which will go finally to a value of b. Okay, that is why b is what is called as a steady state gain. Okay, so I hope it's clear why b is mentioned as the steady state, right? So this is a 2-parameter model. So what are the 2 parameters? The steady state gain and the time constant. Some people will just use the term gain. So, but of course, I prefer the term steady state gain because it's very precise, right? It also tells us what you and I are dealing with. Okay, so typically you will encounter gain and time constant as parameters of first order systems. Now we understand what they are, right? Is it not? Okay, so the gain essentially tells me by what amount I will scale up a step input when I look at the steady state output, and time constant is defined as what we have learned. Okay. Now there is another variant which is also very useful to you and me. Okay, this is essentially this model wherein we still have time constant. We also have the steady state gain B. But what is the new thing that you and I have introduced? We have introduced this parameter TD. Okay, and that is what is called time delay. So what is this time delay? So let us say I give a step input, right? Okay, I give a unit step input, but my output doesn't start to increase immediately from t equals 0. It starts to increase only after a time TD has elapsed. And this TD is what is called as a time delay. Okay, so time delay is, what to say, we perceive it often, right? Is it not? So can you share some example where you would have observed time delay?
So microphone, sir.
Microphone. Okay.
Like when we sing something, there is a system. There could be a delay introduced in the microphone input or output, whatever, to make it more soothing and more, I would say, vibrant.
Throttle pedal operation versus how the vehicle is moving.
All right. Okay. So throttle pedal, even brake pedal, because you and I apply the brake pedal, right? The brake pressure is not going to immediately increase, right? Is it not? Correct. So it is only going to increase from 0 after a certain time interval of time, right? Is it not? Okay. So that's one more application of one more example of the time delay. And even in our day-to-day life, friction, right? If you look at friction in real life, right, what happens? So let's say you and I have a table, right? So we have a table that we want to push, right? So what happens? I apply a force. Will the table start moving immediately? No. No, right? Because why? There's going to be friction at the interface between the table and the ground, right? So when that happens, you can see that there is a time delay, right, between the the point at which a force is applied on the table and the table starts moving, correct? So that is why that's how why we need to consider time delay in certain applications. All right. So I hope all these examples tell us why these why this model, right? Because becomes very important, and this model is typically called as a first order process with time delay. Okay, so typically it is abbreviated as FOPDD. Okay, so this is a very popular model in the domain of process control and also dynamic systems, where when we encounter time delay in physical response, right, we use what is called as a first order process plus time delay model. Okay, so I hope it's clear what this means, right? So now, if you and I look at this model further, this becomes a 3-parameter model. So what are the 3 parameters? The time constant capital T, the steady state gain B, the time delay TD. Okay. So if we take the Laplace transform, what happens is the following. Okay. So in addition to this transfer function B by Ts plus 1, we get a term e power minus TDS, which comes in due to the time delay factor. Okay. So this is an exponential term in the S domain, okay, not the T domain now. Okay, so please remember that, right? So we have gone to the S domain. This is how the Laplace of the time delay comes out to be. Okay, so this is how the Laplace transform works, right? Now the challenge for us is that, like, in here we have n to be 1. The numerator polynomial is of order 1. The denominator polynomial is of order 1, Ts plus 1, sorry about that. The numerator polynomial is e power minus TDS, which is of infinite order. Okay, so you can expand the exponential function as an infinite series, right? And then, we essentially have that coming into play, right? So consequently, we see that, this transfer function, right, is not a proper transfer function. So what was a proper transfer function? What is our definition of proper transfer function?
When the denominator power is lesser than More than denominator power.
Denominator order should be greater than or equal to the numerator order, right? So that is why, we have a proper transfer function, right? So if this happens, we need to do something, right? Because why? Because now here our numerator term is of infinite order compared to the denominator. Denominator is only of finite order, right? So consequently, we need to do some approximation of time delay, and a common approximation, right, of time delay is what is called as a Paraday's first order approximation, where we write this factor e power minus TDS. I have given a very intuitive notion of Paraday's first order approximation, but the Paraday's first order approximation is 2 minus TDS by 2 plus TDS. Okay, so that is the Paraday's first order approximation. Okay, so when you and I have this exponential term which is of infinite order, right? What happens is that we do the Paraday's first order approximation, and we get this, right? We get a finite order approximation. So now, if we plug this one in, what are the values of n and m? N becomes 2, right? Because the denominator polynomial is of order 2, right? Ts plus 1 times 2 plus TDS. What is the value of m? The numerator polynomial is of finite order, 1. And do we have a proper transfer function? Yes, we have, right? We have a strictly proper transfer function, right? So this is the Paraday's first order approximation of time delay, and this helps us to ensure that you and I are able to work further, and go further on in our analysis by having a proper transfer function. Why is this important? Because almost all the analysis that we will do in system dynamics is dependent on the fact that we are going to work with a proper transfer function. Okay, only when we work with the proper transfer function, our tools will be useful, right? So, but then nothing comes free, right? So what is the trade-off here? So the trade-off here is that we introduce what is called as a non-minimum phase zero. So what do I mean by a non-minimum phase zero? If you look at this approximated transfer function, the poles, if you look at the denominator, they are at minus 1 by t and minus 2 by td. Okay, so they are fine. The system is stable. Why? Because t is greater than 0 and the delay time is also greater than 0, right? So both poles are negative. Okay, so both poles are in the left of plane. But there is a 0 now at 2 by 2d td. How did I get this? If I solve the numerator polynomial to be 0, I get s equals 2 by td. Okay, so I have s 0 to be at 2 by td, and since td is greater than 0, the 0 will now be in the right of plane. So if I plot the poles and zeros, okay, of this approximation, I will have a 0 in the right, right real axis. Okay, so that's what we will end up having. So now what happens is that this is what is called as the minimum phase pole or a minimum phase zero, and due to this, what will happen? What is the physics of this? Is it bad? No, I think it's just an approximation, right? It's not going to make the system unstable. Okay, 0 going to the right of plane doesn't mean system is unstable. System is still stable. Please note that system stability is linked only to the poles. But what is the impact which is brought in due to this approximation? Due to this approximation, what will happen is that the system response will look as if the output is going in an opposite direction and coming back to the correct direction. Okay, so that's what will happen. Okay, so what do I mean by this? Imagine, see, the real system is not like this, but imagine a fan being a non-minimum phase zero system. So what will happen? Let's say I come to the room, I switch on the fan. Let us say the fan is supposed to rotate clockwise. What will happen is that the fan will first start rotating counterclockwise, and then after some time it will switch to clockwise operation. Okay. Similarly, if we consider a hypothetical situation, not a reality, let's say a door being a non-minimum phase system. Okay. So what will happen? I push the door. I should expect the door to move away from me, is it not? So if it has a non-minimum phase 0, what will happen is that the door will first move towards me and then move away from me. So that sort of response will happen. Once again, these are only hypothetical responses that come in because of the approximation, okay, not due to real life response, okay. So that is the Paday's first order approximation, and consequently the introduction of a 0 in the right of plane, which is what is called as a non-minimum phase 0, and the consequent physical effect. The consequent physical effect is that we are going to have the response moving in one sense and then going to the other direction. Okay, that is the physical implication. I hope this is clear to all of us, right? Okay. So now we are open to questions. Okay, so we have completed the discussion on today's content. So questions, discussions, we can have. Yes, please. Questions, please.
So am I audible?
Yeah, please go ahead.
Just on the last part only, for the use cases of Paday's approximation method, that means I cannot use that kind of a solution or a solver which is used for solving this particular case of a say suspension system which is going actually in a bump, but it is actually being solved in the case of a rebound. So it shouldn't be happening that way. So
Yeah.
what will be the typical areas wherein we can use it and we cannot use it?
So see, the point is when you have a time delay which is significant, okay, point number one, right? So where the delay time, let's say, is significant when compared to the time constant. So let's say I model a system as a first order system. The time constant is 100 milliseconds. The delay time is only 5 milliseconds. Let's say, I'm just using an arbitrary example, right? So I can say, hey, the delay time is only 5% of the time constant. I may reason out that the delay is negligible and I will neglect the delay. So what will I do? I will go with this model, right? B by Ts plus 1. On the other hand, let's say the delay is 25 milliseconds, right? And the time constant is 100 milliseconds. Now the delay is nearly 1/4 of the time constant. I may not be able to neglect it. So I need to consider it in my analysis. I will go for this with the understanding that, look, during my initial simulation, I'm going to get a response which is not exactly physical. See, obviously, if you going by your example, right, if you have a suspension, right, you go over a speed breaker, right, you are going to expect the suspension to compress, not rebound. So the model may predict rebound, but you essentially neglect it as an artifact, right? You say you know enough to neglect that response, but you are interested in the later part. And this will also help you to do analysis and control. Okay, that is what we gain. Similarly, if you have a brake system, okay, where we use a first order process, right? Let's say we press the brake pedal, you and I will expect the brake pressure to increase, right? Is it not? So if I use the Paday approximation, like it will predict that, oh, the brake pressure is going to first decrease and then increase, right? I don't think that's going to happen in practice. But you and I know enough of the domain to know that I have to neglect the initial part and concentrate only on the later part. So it's once again an engineering approximation. Why? Because if you and I have to deal with this transfer function, the methods that we will be learning are not adequate. Okay. So we are once again doing a very engineering argument and saying that, hey, I know that, like there is a limitation, but however, I will use this Paday approximation and go to a lower order transfer function with which I can work with, right? But I also know that, like the response, particularly the initial phase, is not going to be physically realistic. Why? Because physically it's going to stay like this and then go up, right? That's what is going to happen with an actual system when you have time delay. The output is going to remain at 0, but it's predicting that the output goes in the negative other direction. I won't say negative, it is the other direction. Okay.
Clear, sir.
But sir, let's say a situation comes when the TD value is very less in that way. Then the 2 upon TD value will become very larger in that sense, right, sir?
Yeah, so if the t value is very small when compared to time constant, you neglect this. So what I will do is that if TD is much lower, see, constraints small, big, large, and all are related, right? With respect to it. So the judgment call, the engineering call that you and I need to take is with respect to the time constant. If TD is much smaller than the time constant, what we do is that we neglect the term and we go only with this as our transfer function. That's it. Okay. So we neglect the 2 minus TDS by 2 plus TDS at all. Okay.
Thank you, sir. Thank you.
Any other questions?
Sir, can you just please explain a little bit more on the proper transfer functions and other types of transfer functions?
Proper transfer function, as we know, any transfer function is going to be a ratio of two polynomials, right? A numerator polynomial n of s and a denominator polynomial d of s. Numerator polynomial is of order m. Denominator polynomial is of order n. Okay. Proper transfer function means n is greater than or equal to n. That's about it. Okay. So, and all our methods and all are designed for proper transfer functions. Okay. So, that's the reason why you and I, and by and large, like even most practical systems, the physical phenomena are such that if you and I, it will lead naturally to proper transfer functions. However, when we have this time delay, right, because of the approximation that we do, right, or because of the before the approximation, because of the Laplace of the time delay being e power minus TDS, without the approximation, the order of the numerator polynomial tends to infinity, because see, this is a power series, right? E power minus TDS, right? You can expand to s power infinity. Okay, so what you and I are saying that, hey, we do know that this is going to result in a improper transfer function, but we essentially choose a lower order approximation of this and we work with it. That's what we are doing. Okay.
Sir, what if we represent e power minus TDS as 1 by e power TDS?
So you can have different approximations. See, you can also have e power minus TDS as, like 1 by 1 plus TDS. Okay, this is another approximation. Okay, but what experience has shown in this, the Paddy approximation is more accurate. Okay, that's it. Of course, see, even these are first order approximations valid only when TD is sufficiently small. Okay, so otherwise I need to use higher powers, right? So
Sir, actually, I was like, if we write e power minus TDS equal to 1 by e power TDS.
okay.
So that will go into the denominator. But
okay. I get what you're arriving at. Okay. So once again, what will happen is that, like, you are going to have an infinite series expansion, right? So n goes to infinity. Question is, you need to make a call, right? So this is a mathematical operation. Okay. So but the base function you and I have been given is e power minus TDS by TS plus 1, right? That's what came from the physics, right? Is it not? So that's why we are doing these approximations. This is also a mathematical approximation. You can work with it, but the only point I would want to convey here is that, like, once again, like, if we go for the expansion 1 by 1 plus TDS, the question becomes one of accuracy, right? Which is going to be more accurate? Is it going to be the Paddy's first order approximation or this approximation, right? Which we approximate as 1 by 1 plus TDS. Okay, so it turns out that the Paddy's first order approximation is more accurate.
okay, sir. Thank you.
other questions?
Yeah, so just one query. Here, for example, you told 0 is in the RHP, right? For I mean, for the 0 which was 2 by TD.
Yeah.
So here in this example, assuming TD is a smaller value and then 2 by TD is a bigger value, then this 0 will be little bit farther away from that imaginary axis.
Yes.
What is that significance in the sense? Should it be closer or should it be farther? How will
Okay.
it be in practice?
So once again, the pole in the left of plane being closer to the imaginary axis is what is called as a dominant pole. Okay. To the best of my knowledge, a similar argument doesn't hold for zeros in the right of plane. Just that, we are getting a 0 in the right of plane because of this time delay, right? So, zeros are going to impact the dynamic response as we observed, by impacting the, the residues, right, that come about, right, in the dynamic response function, right? So that's how the zeros will impact, okay? But a question is, if they are closer or farther away, what will be the impact? It's not going to have a very straight correlation like what we studied for dominant poles, okay? Okay, any other questions?
Yes, sir.
Please go ahead.
One thing, sir, I want to clear my understanding, and then one question connected to that, sir. So, like the delay approximation, we already have an existing system. We have a data of delay. Then we are trying to fit it into the curve. So, am I right on that, sir?
So we want to fit it in a lower order model. Okay.
Yes.
So this
Yes.
is the key part, right? So that is, see, instead of an infinite order model for which you and I do not are let me put it this way, the mathematical tools that you and I are going to learn will work
Yes.
for a lower order model. Okay.
Yes.
So, or a finite order model. Let me put it that way, not lower order. Okay. For a
Yes.
finite order model. Okay. So, but then if you and I do not approximate the delay, what will happen is that the model order will be infinite, right? Then how do we handle it? That is the question, right? I hope my point is clear, right? So,
Yes, yes, sir. So one question connected to that, sir. Suppose if we are designing a new system, then that delay has to be considered based on prior experience, or is there any methodology to do so?
So the delay, once again, it comes from the physical system, right? So if you design a new system, let us say
Yes.
we go to, let's say, a brake system, right? You had a
Yes.
initial brake system with that significant delay. Let us say the time constant of the brake system is, let's say, 100 milliseconds. I'm just taking
Yes.
around, right?
Yes.
And the delay to
Yes.
begin with was 25 milliseconds. But now you design some fast acting valves, right? Due to which
Right.
you brought the delay to 5 milliseconds. Then what
Yes.
you and I argue is that, hey, you know what? Previously we had a larger delay, but we brought
Yes.
it down, right? So
Yes. Yes.
consequently, now you and I can neglect it and we can go ahead,
Yes.
right? So once
Right.
again, see, whether we need to consider the delay or neglect the delay comes from physical considerations, okay, not necessarily from mathematics, right? The physical considerations dictate whether you and I have to consider the delay. Okay, I hope the point is clear, right? So,
Yes, sir. Yes, sir. Very clear, sir. Thank you, sir.
yeah, welcome.
Sir, so for the same system, time delay is independent of the steady state gain.
Oh, so time delay is a separate parameter. Once again, see, these are two physically different parameters, right? So the question is whether we want to have a correlation or something like that is a different question, right? So the broad question is that, like, see, time delay is coming out of the characteristic of the system response. The gain is another characteristic of the system response, right? So to begin with, there is no direct one-to-one correspondence between them. Okay, yeah. Okay, so they are two different characteristics of the same system. All right. Okay.
Okay, sir.
Okay. So I think let me quickly take attendance for today's class. Aditya Kumar, no.
Present, sir.
Anand, no.
Yes, sir.
Ananta Kumar,
Yes, sir.
Arunachalam,
Yes, sir.
Hassan, no. Hemant,
Present, sir.
Jagan,
Yes, sir.
then Kesav,
Yes, sir.
Lakshmi Narayanan,
Present, sir.
Prabhakaran, Karim Vinayak,
Yes, sir.
Rahul,
Yes, sir.
Roshan,
Present, sir.
Sabish, Satish,
Yes, sir.
Titus,
Present, sir.
Vallish,
Yes, sir.
Vigneshwaran. Vigneshwaran? Is Vigneshwaran here? Okay. Vijay Raj.
Sir, Hassan present, sir.
Who's present? No.
Hassan present, sir. Just some network issue got disconnected, sir.
Sir, and Vigneshwaran is also on call, sir. Like,
Hello, sir. Present, sir.
Yeah.
I think I forgot to unmute. Vignesh is
Sure,
present.
sure. Okay. Vijay Raj,
present, sir.
Vikas,
Present, sir.
Vivekanand. Vivekanand? No.
Present, sir.
Ramanand.
Present, sir.
Present, sir.
Yuvraj.
Present, sir.
Everyone is present. So then we will continue tomorrow. Okay. So thank you.
Thank you,
Thank you,
sir.
sir.
Thank you. Thank you all.
Thank you.
Thank you, sir.